For our project, we use the SolidWorks flow simulation add-in. Specifically, we're going to go over free convection or natural convection of a solid body. The very first thing you're going to need to do is create your body. I did mine in an assembly, and it could be either a tube or a cube or any solid body. For this one, we're going to use a cube, and then I created two openings, one at the bottom, one at the top. This one I'll use as my inlet. This will be my outlet. Next, after this is all done, you're going to have to enable the SolidWorks flow simulation add-in. So you're going to go over here under options, you're going to click add-ins, and then scroll down and you'll see SolidWorks flow simulation 2020. Just make sure to check that box, click OK, and then momentarily the flow simulation tab should become available, which you see here. All right, once you've enabled flow simulation, the first thing you're going to do is click on Wizard. This will allow a new project to be formed. I'm going to name it Natural Convection and Conduction. Next, you'll pick your units that you're going to use. I'm just going to use USA units. For this, we'll be doing internal flow analysis. We'll leave this exclude cavities without flows checked. Since we are going to do some conduction, we'll click on that. We'll have no radiation, no time dependency. We will click on gravity since we want to have a buoyancy effect, which allows for natural convection. We'll have no rotation and no free surface. This is key just to make sure that it's oriented correctly. I already went through and I found out that the z-axis is where I want my gravity to be, in the negative direction. Next, you're going to pick your liquid. We're going to use air. So just double click on it. Now it's enabled. We're going to keep it on laminar and turbulent. That allows SolidWorks to correctly determine what it is during the analysis. I click next. For this situation, we're just going to use like a particle board or plywood. So you click under building material. This will be for all the material of the walls. There's many different ones you can select from. The next one is the thermal wall condition. For this project, we're going to leave it at adiabatic since we'll declare our boundary conditions independently. And then lastly, we determine our initial conditions. So for this situation, we're going to have the air temp be a little colder outside. So we'll put it at 28 degrees. That way we get our natural convection. And the solids, we're going to start with it at the default of 68 degrees. We finish. Okay, so after you click finish in the wizard, this will pop up. It's basically saying that your body is not closed and it's not watertight. It gives you the option to create a lid, which will close the body. SolidWorks has a tool specifically for this. I'll show it to you, but it doesn't always work. It's usually in your best interest to create your own lids manually, which I'll go into. So I'll click yes. This works a lot of the times if you extruded just a solid like a tube, opposed to this, which has been assembled via mates. So it's asking you to select the surface that is open. SolidWorks finds the hole, and then you would click close. For this, we're going to actually create our own lids, which I already did. I'll just go into it and explain a couple of the features. So I'll unsuppress. It's identifying that it could run because the geometry has changed. I'm not going to correct it because it's still open. Go in here, and when you extrude, you want to extrude about the midplane, and then just choose a reasonable distance. And that's the key thing when creating a lid. So I'm going to close this out. and I'll unsuppress the other lid. Now that we have lids on both of our entries and exits, the flow simulation can tell the geometry has changed, and if we should reset our computational domain. So we're going to click yes, and then yes again to start the computation. Now your body is completely watertight due to the lids that you have created. Okay, the next thing after we created our lids is to set up some of our input conditions. So I have some pre-set up conditions. We're going to start with our boundary conditions. We're going to start with the inlet down here first. So you select the face, as I did right there. Under type, you can do different openings, either velocity, mass flow. For this, we're going to click under pressure openings and just set it as environmental pressure. We're also going to have it as the same temperature as we did in our initial input settings under wizard. Okay, so that's for the inlet. Now for the outlet, same thing. Click on that face. You're going to do pressure openings, environmental pressure, same temperature. The last one, which will get our natural convection actually flowing, will be a wall temperature. So I selected this inside bottom wall, and then underneath here of types, you're going to click on wall, real wall, and then I'll just do the same initial temperature that the solid body will start at that we did in our initial settings under wizard. But this bottom piece will remain that same temperature throughout the study. Okay, the next input data that we're going to do is goals. And goals outline what the project, when it runs, actually will pay attention to and analyze. So for us, we're cared about the temperature of the fluid, and I'm going to do the average value. I'm also going to do the maximum temperature of the fluid. And then two more, same thing, for velocity. And there is a whole list of parameters that we can select from. And the last one was maximum velocity. After you set up your input data of the boundary conditions and goals, you then can run your project and start your analysis. One last thing, though, I want to cover before I do that I found helpful is if you right-click under input data, you can show gravity as an arrow. And for this, with the natural convection, it can be really helpful. So you're going to go up to your projects, and you're going to click on natural convection and conduction, run, solve. We're going to do a new calculation. We're going to click run. A window will pop up here. And depending on your analysis, this can take some time. All right, it's finished, and there's no warnings, so that's good. We're going to close this out. The last thing I'll cover is the results. So down here, you can click on the results tab. There are many different options that you can do. I'll only cover three due to the length of the video. First one we're going to do is a cut plot. And I've done three different ones. Let's click on this first one. So this first one I did is of the velocity. You're going to select a plane. I selected the right plane, which cuts through uh, the body. I'm going to do it with vectors. You can do a contour, isoline, streamlines, or mesh. And then to select velocity, it's just this option right here. And there's many different ones that you can go through. And then the rest I just left how it is. And I clicked OK. And there it is. It's just a 2D plot. I'm going to do the same for temperature. Right plane, same. This one I did contours. And then down here, I did the temperature of the fluid. I'm going to hide the one of the velocity. And then there is the temperature of the fluid. Hide this. I'm going to do a surface plot. I just selected the 4 faces on inside of the box. And I'm going to do contours. And then down here, I selected temperature of the fluid. Now you can see the temperatures of the wall surface. And then up here is your chart. I'll actually go in and show you one last thing. Right here, you can adjust the minimum and the maximum temperatures for your key. The last results that I'm going to do is flow trajectory. Edit definition. For this one, I did it about the front plane. And then I did it as pipes. Static trajectory of the velocity. Okay, it's got to run. Hide the wall. Oops. And there's the flow. Last thing on results I'll show you is you can actually have it play as an animation. And if you so chose and you wanted to export it, you could come in here and export, save as, and you can edit it under animation. And that covers the basic flow analysis of natural convection with conduction.
There are many other ways for analysis depending on the model or application, as well as displaying the results. A member in the group is part of the active cold roof capstone. These steps were used to get meaningful simulations to show airflow, as well as the temperature of the airflow. The analysis was last semester, so these animations will be used to visualize the flow. The airflow between the original roof and the new outer roof takes a majority of the heat away from the outer roof and the snow. This reduces the chance of snow on top from melting, then refreezing in a colder location and potentially causing damage. Ice dams have been known to fall and destroy cars, decks, and on the rare occasion, people. The existing cold roof system that our sponsor in Big Sky has is a pitched roof using natural convection. This flat roof has a slope of 1/12. As you can see, the air heats up more quickly since the flat roof has a smaller CFM due to the forces of natural convection. The next roof has a fan added with a fixed CFM of 93 to improve the performance of this roof. The 93 was a part of a previous calculation for a 50-foot long roof to keep the exterior below 32 degrees Fahrenheit.